My name is Ian McGregor, and I'm going to talk to you today about leveraging multi-source data to improve near real-time forest disturbance monitoring. So identifying deforestation as it happens, or in near real time, is a challenging task in remote areas. After all, if you're not actively living in the area, then it can be easy for loggers to extract timber and leave before someone finds out. But even though it can be quick, the overall impacts can be severe. This is especially true in Myanmar, which has high levels of deforestation, despite being one of the most forested countries in Southeast Asia with high levels of biodiversity. Let's take one of the country's protected areas here as an example. Our best approach for finding near real-time disturbances depends on satellite remote sensing. Current methods, while helpful, tend to rely on binary alerts, where either an event has happened, or 1 here, or it has not happened, 0. Our research aims to answer the question, can we find a way to simultaneously increase detection accuracy and reduce detection latency by monitoring these forest disturbances in near real time? Although the ideal answer is yes, we hypothesized there would be ultimately a trade-off between these two objectives. So we tested our idea over multiple training points with known disturbance dates. Using the coordinates from those, we obtained multi-source satellite data from which we identified trends and deviances from those trends before combining into a single aggregated time series. To do so, we fit a time series model to each satellite sensor's pre-disturbance data to show us the expected trends. And we then compared those to what actually happened post-disturbance. If our code detected large persistent changes after the disturbance, we would say our probability of disturbance has increased. However, moving from these trends to a distinct probability requires quantitative choices which, as we hypothesized, would lead to trade-offs. So we found support for this hypothesis, where we do not have an optimal scenario that yields the best accuracy and the lowest latency. We instead have a situation where, at one extreme, our code detects disturbances within about 4 days of the event, but it has a false positive rate of 8%. At the other extreme, we detected disturbances in roughly 10 days, but with false positive rates of 5.8%. Here, false positive refers to the detection of a disturbance when in truth there wasn't one. So why does this matter? Well, our method is novel in 2 major ways. First, using multi-source satellite data reduces our detection latency by giving us temporally overlapping observations. This is crucial for a monitoring paradigm where we want to use as much satellite data as we can to get the clearest picture of what's occurring on the ground. Second, we're using probabilities instead of a binary alert, which allows local forest managers to allocate resources as needed. Perhaps in a real context, there are more than 1,000 possible forest disturbances that need to be checked, but there are limited resources to do so. Having probabilities allows these forest managers to focus their attention on only the highest concern areas. So what's next? Well, at the outset, we want to expand our model to include biogeographical and socioeconomic data as covariates, because as good as the probabilities are, we hope that including situational context can significantly improve the probability estimates. And the way that we'll do this is by incorporating Bayesian methodology, whereby the prior situational context of a specific area influences its current probability of disturbance. This includes the covariates, the prior remote sensing data, and the probability of disturbance of nearby points, all of which are then combined with the new remote sensing data to give that updated current probability. Finally, we want to put these efforts in the hands of the forest managers themselves. Our plan is to create an app whereby they can confirm or reject in the field that deforestation has occurred. This will automatically update the underlying model, serving to both continuously improve that model over time, plus allow them to be their own data user and data producer. Our hope is that upon success, this method can be applied anywhere else in the world where an ecosystem disturbance is detectable via satellite imagery. Thank you.